Hello, everyone. I'm Ryan Keeley, currently working as a postdoc at UC Merced. I'm happy to be back for another Cosmology from Home conference. So first, I would like to thank the organizers for organizing this conference and you all listeners for your attention. So I'm broadly interested in testing the lambda CDM model, where in past Cosmology from Homes, I've talked about testing the lambda part. This time, I'll be talking about testing the CDM part. There are a few common ways people hunt for dark matter, often summarized by plots like this. The SpiderMan diagram imagines dark matter has some coupling to the standard model, and thus different directions time would go indicate different dark matter standard model interactions, and thus the different detection techniques. Time going down would indicate dark matter annihilating into standard model particles, and thus indirect detection. Time going to the right would indicate dark matter scattering off standard model particles, and thus direct detection. And time going up would indicate dark matter particles being produced from standard model particles, as in colliders. That is, you can break it, shake it, or make it. But rather than all that, I investigate dark matter in astrophysical environments. And since astrophysical environments are probing only its gravitational interactions, I suppose you could say I would weigh it, though that sort of breaks the rhyme. There are a range of astrophysical probes of dark matter, as listed here, and they all tend to test dark matter in rather phenomenological ways, as in, rather than testing the specific identity of dark matter, they test whether dark matter self-interacts or how it clusters. Indeed, most of these tests of dark matter work by trying to identify the smallest dark matter halos. I'm going to elaborate about how to use strong gravitational lensing to characterize the population of the lowest mass dark matter halos and hence constrain dark matter properties. Okay, so in strong gravitational lensing, the light from a source is deflected by the combined gravitational potential of the main deflector lens and all of the subhalos and line of sight halos along the trajectory the light follows to create multiple images of the source. Strong lensing probes of dark matter work by analyzing the magnifications and distortions of images to reconstruct or infer the distribution of dark matter. To build some intuition, since deflection is proportional to the first derivative of the potential and magnifications are proportional to the second, then the image positions constrain primarily the model of the main deflector, and the magnifications are sensitive to all of the subhalos and line of sight halos. So there are two common techniques for inferring dark matter from strong gravitational lenses, gravitational imaging and the flux ratio anomaly method. Gravitational imaging uses larger source sizes, which create extended arcs, and you look for dark matter in the distortions of the arc. Alternatively, there's the flux ratio anomaly method, which is used when the size of the source is sufficiently small, such that 4 distinct images can be created, and rather than an extended arc. Analyzing the fluxes of these images can allow us to make inferences about the mass function of low mass dark matter halos. It is this last technique that I'll be focusing on for this talk. And so one of the simplest cases for dark matter that we can test with a strong lensing probe is warm dark matter, where CDM predicts an abundance of dark matter halos at small masses. Warm dark matter predicts few. That is, the free streaming of the warm dark matter particles suppresses structure at small scales. To find what scales are suppressed, the general idea for constraining warm dark matter is finding the smallest dark matter halo. So warm dark matter typically has masses on the orders, dark matter masses on the order of a keV, such as like sterile neutrinos. All right, so when talking about observing small-scale structure, one has to move away from the matter-power spectrum and instead talk about the halo mass function. So CDM has a power law halo mass function that can, in principle, continue to arbitrarily small masses, whereas warm dark matter's halo mass function is suppressed. The parameter that characterizes this suppression is the half-mode mass, as in the halo mass where the warm dark matter suppression is a factor of 2 compared to CDM. This connects back to the particle physics and the identity of dark matter in that the half-mode mass is related to the mass of the dark matter particle. This equation here is specifically for a thermally produced dark matter relic. So for our purposes, we use quasars as sources. Like I mentioned previously, source size matters. The smaller sources are in principle more sensitive to smaller mass dark matter halos. But of course we don't want too small to avoid microlensing by stars. The cold, dusty torus and narrow line emission regions of a quasar work well for this measurement for these 2 points. So to summarize the ingredients of our methods, we use the flux ratio anomalies of quadruply imaged strong gravitational lenses to constrain the halo mass function and thus constrain warm dark matter and set lower bounds on the dark matter mask. So now we ask, can we constrain arbitrary halo mass functions, as in beyond either CDM or warm dark matter? And so to be concrete about this, I'm introducing the mixed dark matter model. So I'm asking the question, can we use strong gravitational lenses to tell the difference between a half warm and half cold case, and tell the difference between that and either a full warm dark matter or a full cold dark matter? In such a model, the CDM component could still collapse to arbitrarily small dark matter halos, but the warm dark matter component would still categorically suppress the amount of structure with respect to CDM. The point of this work isn't to justify something like the cosmological dark matter being half WIMPs and half stellar neutrinos in an a priori sense. The point is to demonstrate that these strong lens systems can tell the two apart. So in the flux ratio anomaly method, the observable model predicts is not a specific value for the flux ratios, but a distribution. This is because the specific distribution of the dark halos is not parameterized, just the statistical distribution of them is. Thus, we need novel statistical techniques, for example, simulation-based inference. But people often call it likelihood-free inference or implicit likelihood inference, if that's more familiar. The figure here demonstrates this point, as in for a cold dark matter model, warm dark matter, and mixed dark matter model, there's a distribution of flux ratio values that would be predicted for one particular lens. So when one observes the real flux ratio values for the lens, the likelihood of the observation is determined by where the observation would fall in these distributions. And so the signature of CDM is that the predicted distribution is more broad, as in there are more halos to lens the image, and so there's so the different realizations of that distribution can have a larger range of values. And conversely, then the signature of warm dark matter is that the predicted distribution is much less broad, and of course, mixed dark matter is by construction intermediate. To compress the information in these distributions, we introduce the Z-statistic, which summarizes how different the simulated flux ratios are from the flux ratios predicted by the bare main deflector, which I refer to as the reference flux ratios in the equation here. So with the Z-statistic, we can begin to answer the question, can we tell the difference between mixed dark matter and warm dark matter with our strong lenses? Plotted in the figure here are the distributions of the predicted simulated Z-statistic for various warm dark matter and mixed dark matter models of various half-moon masses. So I'd bring your attention in particular to the orange and blue curves here. The fact that these distributions are almost identical for these values of the half-moon mass for the two models would indicate that the two models are indistinguishable. So this can be interpreted as the mass function being similar in halo mass ranges that contribute to most of these observables. However, this result is for one particular lens configuration. So the question becomes, perhaps these models could be distinguished if we use multiple different configurations of lenses. The two lens configurations I'm doing this test with are shown here, with the image positions, flux ratios, and the critical curve. The previous figure for distributions of the Z-statistic was made with the top lens configuration, and the test now is to remake that figure with the lens configuration on the bottom. The idea is that different configurations of a gravitational lens will probe different parts of the halo mass function, and thus help break degeneracies between the warm dark matter model and the mixed dark matter model. So here we see the results of that test. The blue and the orange refer to a warm dark matter model with a half mode of 10 to the 9.5 and a mixed dark matter model with a half mode of 10 to the 10. So the first lens configuration, they predict the same distribution, but for the second, the distributions are shifted with respect to the other. Thus, multiple kinds of lenses are necessary to break degeneracies between these models. Now that we have a proof of principle demonstration that we can differentiate between the warm dark matter model and a mixed dark matter model, I'm going to walk you through how we can do basically the full calculation for how we do our analysis. So the basic idea here is that instead of using these Z-statistics, we're going to be calculating essentially a posterior for the mixed dark matter model for some mock data, and then see if whether the f equals 0 or f equals 1 as set of parameters. So essentially either the pure cold dark matter or pure warm dark matter, if either of those parameters, like those ends of parameter space would be rolled out using our using our mock data and our analysis method. So like I mentioned previously, we have to use basically a simulation-based method, and so that's the specific statistical method we're using is called the ABC method. So the typical steps are that you first have to first sample the prior parameter space, and basically the parameter space itself is allowing you to calculate a mass function. So with the mass function again is just the statistics of essentially the population of dark matter halos. And so the next step is to then populate your lens with a specific realization of line of sight and subhalos. With these halos in place, you can then do the ray tracing and hence the lensing calculation. And from all this lensing, you can calculate what the fluxes of the image should be, and hence the flux ratios. With the flux ratios, we can calculate then what we call a summary statistic. So basically, if you have your set of three flux ratios, you can compare them to the data, F data here in the equation in the bottom right. And if that summary statistic is basically within a predefined threshold, then you say that the parameter that gave you that S statistic is then accepted. And so the distribution of the accepted parameters is your posterior. And we can see the results of this forecasting here. So the basic idea is to generate mock data from a mixed dark matter model. So the posterior parameters is what's shown here, where sigma sub is basically just a parameter that sets the normalization of the sub-halo specific mass function. So in principle, because cold dark matter, even in that simplest dark matter model, we don't really know how essentially small scale things should affect subhalos. In principle, so sigma sub is supposed to capture physics like stripping of type of subhalos, and essentially destruction of them. So the other parameters are ones I introduced previously, the half moon mass and the fraction. To build some intuition, the f equals 0 and the half moon mass of 10 to the 10 corner and are basically is the corner with the least amount of substructure, as in the warmest. So with like a sigma sub of 0, you have essentially no subhalos, and with a half moon mass of 10 to the 10, then basically all the populations of halos 10 to the 10 and below are suppressed by a large amount. And so of course this is the corner with the least amount of structure. And the opposite corner, f equals 1 and a half moon mass of 10 to the 4, and a sigma sub of 0.2 would be the one with the most amount of structure. The green line shown here are basically the true parameters that we used to generate the mock data. So basically the true point is basically an intermediate case, where we have a fraction of around 0.5. We have an intermediate number of subhalos, and the half moon mass is basically just above where the current limits set for warm dark matter. And so in principle, and so one simple result is that our calculated posterior does essentially recover the true true input set of parameters, and then also probably the more important result is that f equals 1 is so essentially the pure cold dark matter case is basically very ruled out. But slightly important. So essentially for the number of lenses that we use here, so essentially the warm dark matter case is less ruled out. It's basically harder to it's harder to rule out purely. So basically this essentially arises from the fact that there's parameter degeneracies between between the parameters that we're using here. So basically you can see essentially the shape of the degeneracy in the posteriors themselves, so essentially the true intermediate amount of structure here can either be interpreted as being coming from either a small amount of substructure in particular, or some suppression in the total amount, whether that's coming from essentially it being mixed or from it being purely warm, is slightly hard to disentangle. The next thing we calculate is the base factors for the mixed dark matter relative to the warm dark matter, for a varying number of lenses used in the analysis. So that's what's shown here in this figure. So the blue line is the base factor you would get for using the simple number of lenses. When you get to around 40 lenses or so, you can get a base factor of 30 to 1 for mixed dark matter to warm dark matter. I'm involved with a JWST program that will observe 31 lenses in particular. And so the red line shows the forecast for our specific program, where we should get around a base factor of 13 to 1 for our 31 lenses. We're around halfway through our JWSC program, where we currently have 15 or so lenses, and the data reduction is currently being done. Our first paper basically describing our program, and basically the results for the first lens is soon to be put on the archive, and we expect by the end of the summer we should essentially finish the data reduction for our 15 lenses and include a dark matter interpretation of our results, potentially including constraints on warm dark matter and potentially even self-interacting dark matter. So look forward to that in the future. And so that brings me to my conclusions, where I would want to highlight that with our analysis, potentially arbitrary mass functions can be constrained with the right kind of strong lenses. So dark matter models beyond CDM and warm dark matter can be constrained this way. There are, of course, large parameter degeneracies that make this inference problem hard. And so we need to essentially refine our predictions for the subhalo distributions, which is ongoing work being done with graduate students in my group. And so we can also use information from other probes, basically other source sizes, and from information from extended arcs to again help nail down this inference problem and make even more robust constraints. Thank you for your time, and thank you for your attention. Goodbye.